All right, let's dive into a topic that is quite literally everywhere. It's in your morning coffee, it's in the engine of your car, it's in the chemical reactions that are happening inside you right now. We are talking about the science of energy itself, thermodynamics. I mean, think about it for a second. It's something we see every single day, right? You pour a hot cup of tea, you get distracted, and when you come back, it's cold. You grab a soda from the fridge, and it slowly gets warm. It feels totally normal, but why does it always work that way? Why doesn't your cold drink ever get colder on the kitchen counter? Well, the answer is hiding in the fundamental laws of energy, and that's exactly what we're going to unpack. So, this field of science, the one that answers why your coffee gets cold, has a name: thermodynamics. Honestly, you can just think of it as the official rulebook for how energy, heat, and work play together across the entire universe. At its very heart, thermodynamics is all about watching how energy moves around and changes form. And if you're a chemist, this isn't just interesting, it's everything. We use it to follow the energy in a chemical reaction. Does a reaction spit out a bunch of energy and get hot, or does it actually need to absorb energy just to get going? Thermodynamics gives us the tools to figure that out. Okay, so if we're going to track energy, we have to get really specific. We can't just study everything all at once, right? So scientists came up with a really simple but super powerful way to define exactly what we're looking at. It all starts by drawing a line between your system and everything else, the surroundings. It's really as simple as this. Imagine just drawing a circle around whatever you want to study. The stuff inside that circle, that's your system. Everything outside the circle, and I mean everything, is the surrounding. And that line you drew, that's the boundary. It's the most important part because that's the border where all the action, all the energy exchange actually happens. Let's make this totally real. Picture mixing two chemicals together in a glass beaker. The chemicals themselves, the stuff that's actually reacting, that's our system. The glass beaker, the lab bench it's sitting on, the air in the room, even you watching it, all of that is the surroundings. This simple separation is the absolute starting point for any calculation in thermodynamics. And the type of boundary we draw actually defines the system. So an open system, like a pot of boiling water on the stove, lets both energy, that's the heat, and matter, the steam, escape into the room. Now, if you put a lid on that pot, it becomes a closed system. Heat can still get out through the walls of the pot, but the water itself is trapped inside. And finally, the goal, the perfect ideal, is an isolated system, like a perfect thermos. In theory, absolutely nothing, no heat, no matter, can cross that boundary. All right, so we've defined our little corner of the universe. Now we need to learn the language to describe what's happening inside that space. We need a way to measure its properties and keep track of how it changes. And that brings us to some really key concepts. So when we talk about properties, they basically come in two flavors. On one hand, you have extensive properties. These depend on how much stuff you have. So 2 liters of water has twice the mass and twice the volume of 1 liter of water. Makes sense, right? But on the other hand, you have intensive properties. These couldn't care less about the amount. The temperature and the density of that water are exactly the same whether you've got one tiny drop or an entire swimming pool full of it. Now pay close attention because this next idea is absolutely crucial. A state function is kind of like your bank balance at the end of the month. If you start with $10 and you end with $100, your net change is $90. It doesn't matter if you got there with one huge deposit or 1,000 little transactions. All that matters is where you started and where you ended. A path function, though, is that list of transactions. It's the specific journey you took to get there. And this is so important because in thermodynamics, the total energy of a system is a state function. But the two ways it can change, as heat and work, are path functions. Which, of course, brings us to the next big question. We know energy is moving across that boundary we talked about, but how? Well, it turns out there are really only two fundamental ways for this to happen: as heat and as work. So energy moves in two main ways. The first one is heat, which is just energy transferring because of a temperature difference. It always flows from the hot thing to the cold thing. The second way is work, which is a more orderly mechanical transfer of energy. And the classic example is right here: a gas trapped in a cylinder with a piston. If that gas inside expands and pushes the piston up, the system is doing work on the surroundings. But if some outside force pushes that piston down, compressing the gas, then the surroundings are doing work on the system. Both are just ways of getting energy across that boundary. Okay, we've defined our system, we've got the language down, and we know how energy can move. So now it's time. It's time for the single most important, most fundamental rule that governs every bit of this. Let's talk about the first law of thermodynamics. This is it. This is the big one. It's the law of conservation of energy. And it's a truly profound statement about our universe. What it's saying is, you can't get energy for free, and you can never, ever truly get rid of it. All you can do is change it from one form to another, like from the chemical energy in gasoline to the kinetic energy of a moving car. The total amount of energy in the universe is and always will be constant. And here is that beautiful, powerful law in a simple equation. The change in a system's total internal energy, we call that delta E, is just the heat you add to it, which is Q, plus the work done on it, which is W. That's it. It's a perfect energy budget. Every single bit of energy has to be accounted for. It either came in as heat or it came in as work. So that equation is always true. It's a fundamental law, but measuring both heat and work can be a little tricky in the lab. So chemists, who are practical people and often run their reactions in beakers open to the air, came up with a really clever shortcut to track energy. It's called enthalpy. Now, formally, enthalpy is defined as the internal energy plus the product of pressure and volume. But here's what you really need to know. What we almost always care about is the change in enthalpy, or delta H. Because for a reaction happening at a constant pressure, which most lab reactions are, delta H is exactly equal to the heat that was either released or absorbed. It lets us just focus on the heat. And that flow of heat can go in two directions. If you look at these little energy diagrams, you see two different stories. In an exothermic reaction, the system releases heat into the surroundings, which is why it feels hot. The products end up at a lower energy level than what we started with, so that change, delta H, is a negative number. The total opposite is an endothermic reaction. This one has to pull heat in from the surroundings to even happen, which makes things feel cold. Here, the products are at a higher energy level, so delta H is positive. This is all great if you can just stick a thermometer in your beaker and measure the heat change. But what about a reaction that takes, say, 1,000,000 years? Or one that's explosive, or maybe one that produces really nasty byproducts? How in the world do you find the energy change for that? Well, you use an amazingly clever little trick called Hess's law. And the whole reason it works goes back to what we said earlier. Enthalpy is a state function. Remember, it only cares about the starting line and the finish line, not the path you took to get there. So Hess's law says if you can get from your starting chemicals to your final products through a whole series of different reactions, the total energy change will be the exact same as if you did it in one single step. This diagram here shows it perfectly. Let's say we want to get from our starting point A to our final product Z. We could take the direct route, path A. The energy change for that path is Q. But maybe that path is impossible to do in the lab. So instead, we could take an indirect route, path B, going through steps B and C first. Hess's law is our guarantee that if you add up the energy changes for each of those smaller, measurable steps, that's Q1, Q2, and Q3, that total will be exactly the same as Q. And this is why it's like a superpower for chemists. It means we can take a bunch of simple, safe, easy-to-measure reactions and add and subtract them like algebra problems to figure out the energy change for a reaction that is way too dangerous or difficult to ever measure directly. It's a beautiful, practical application of a fundamental idea. So we've covered a ton. We know energy can't be created or destroyed. But that brings us right back to our very first question. If the total energy is always conserved, why does a hot coffee always cool down? The total energy in the room is the same. It's just been moved around. So what's the invisible force pushing change in that one specific direction? What makes things happen spontaneously at all? Well, that, my friends, is a story for the second law of thermodynamics.